Hello students, in this lecture we will explain satellite link design procedure. Here there are total 5 steps in the satellite uplink design. So consider this figure, that is a high power amplifier, then this is a earth station antenna, and when power is transmitted different losses are there. So this antenna mismatch loss is denoted by AML, then transmitter feeder loss is denoted by TFL, polarization loss PL, then atmospheric loss A, free space loss in uplink FSL, and gain of satellite is denoted by G-sat. Here power of this high power amplifier is denoted by PHPA, and gain of antenna is a GES, and this is a transmitter feeder loss. So by using this figure we will explain the procedure of satellite uplink design. So first step is the EIRP, that is the effective isotopically radiated power, which is given by power of high power amplifier plus gain of this earth station antenna, minus transmitter feeder loss. This bracket denotes all the terms are in dB. Then next is a step 2. In this step 2, this effective isotopically radiated power when transmitted from earth station to satellite, then different losses are there, and in this we have to calculate transmission path loss. This transmission path loss is summation of all these losses, that is TPL is equal to FSL plus AML plus PL plus A, that is the atmospheric loss. That is the summation of all these losses. Then next is the step 3, carrier power at satellite. That is we have to find out carrier power or receive power at satellite, which is given by EIRP minus transmission path loss, as we have derived in this equation. Step 2, TPL plus gain of satellite minus receiver feeder loss. But generally power of signal at satellite receiver is equal to power of carrier, therefore C is equal to PU. Then next step 4, we have to calculate noise power and C by N ratio. Noise power generally given by N uplink is equal to KTB, that is the temperature of satellite. Then C by N ratio is given by, we have to fill up the value of C is equal to PU, that is a C is equal to PU, and N is equal to KT sat B, that is a KT sat B. Then all these terms are in dB, we can write P minus KT sat B. We have to fill up the value of P uplink from this equation, that is this equation. So fill up the value, we will get EIRP minus TPL plus G sat, that is fill up all these values, minus RFL minus, this equation can be written as minus K minus T sat minus B. So in this equation observe this term G sat minus T sat is there, and we can denote this term G sat minus T sat is equal to G by T, and fill up that value in this equation. Then same equation is there, only fill up the value of this, that is a G by T in this equation. Then next is a step 4, carrier to noise power density ratio, and in this, as previously mentioned, noise power is given by KT sat B, that is the temperature of satellite, B is a Boltzmann constant, and K is a constant, K is a Boltzmann constant, and B is a noise, noise bandwidth. So let noise spectral density N0 is given by, N0 is equal to Pn by B, put the values, we will get KT sat. Therefore C by N0 is equal to Pu upon KT sat, we can represent it as a P uplink minus KT sat. Again fill up the value of Pu from this equation, that is a whole equation we have to fill up in this equation. Fill up whole equation, we will get this equation, and again KT sat term is here denoted as this, that is a K minus T sat. Again here two terms K sat minus T sat, denote it as a G by T, and fill up the value of K, that is K is a Boltzmann constant denoted by 1.35 into 10 raised to minus 23, and if we will calculate we will get minus 2 to 8.6, and fill up that value in this equation, that is a K value we have to fill up. We will get last equation C by N0, that is noise power density, is given by this equation. So this is a design uplink design procedure, and we have explained in detail this satellite uplink design.